All right, good evening, everyone. We're going to give just a moment to allow people to join us before we get started. Just one quick moment. I know we have a lot of interest in tonight's program. A lot of people sign up. Okay. While people are still filtering in, I'm going to go ahead and start tonight's introduction. So I just want to say good evening, everyone, and welcome to tonight's virtual event with author and Harvard astrophysicist, Dr. Avi Loeb. Avi will be joining us tonight to talk about his new book. It just came out at the end of August, Interstellar, The Search for Extraterrestrial Life and the Future of Our Stars. And I actually have our audiobook copy of the libraries right here. I enjoyed listening to this on audio. Before we begin, please know we have many wonderful author programs and other events for adults on our schedule. A full list of our current events is available to browse at hudsonlibrary.org. Many of us are looking forward to our series next month that will explore Japan through arts, culture, and history, as well as our upcoming virtual author event with Laura Norton, who's going to talk about her new book, Lay 'Em to Rest, which is all about forensic pathology and analysis. So if you're interested in cold cases and stuff like that, it's totally up your alley. Now, copies of Avi's book are available for purchase courtesy of Hudson's own independent bookshop, The Learned Owl, and we will add a link in the chat for easy purchase. We would also love to hear your questions about tonight's topic, so please leave your questions for Avi using the Q&A located in the bottom of your screen, and we will get through as many as we can towards the end of the event. Now, I am pleased to introduce tonight's speaker. He has lots of credentials. I'm going to try and get through as many as I can. Avi Loeb is the Frank B. Baird Junior Professor of Science at Harvard University. He's also the longest-serving chair of Harvard's Department of Astronomy, the founding director of Harvard's Black Hole Initiative, and the current director of the Institute for Theory and Computation within the Harvard-Smithsonian Center for Astrophysics. He also heads the Galileo Project, chairs the advisory committee for the Breakthrough Starshot Initiative, and is former chair of the Board on Physics and Astronomy of the National Academies. He's the author of 8 books and more than 1,000 scientific papers, and is also an elected fellow of the American Academy of Arts and Sciences, the American Physical Society, and the International Academy of Astronautics. In 2012, Time selected Loeb as one of the 25 most influential people in space. So I'm really looking forward to hearing his research and his thoughts about tonight's topic. So Avi, thank you so much for joining us this evening, and I will give the screen to you.
Thank you very much for inviting me. It's a great pleasure and privilege. So let me share my screen. I'll show some slides, and I'll be glad to answer any questions you might have. I will describe content that goes slightly beyond my book to give you the latest developments in my research. Altogether, it's a new frontier of science, and it involves interstellar objects. These are objects that came from outside the solar system. For the first time, we discovered such objects over the past decade. And my interest in this frontier is to find technological needles in this haystack of rocks that we may have, because we know that within the solar system, there are plenty of rocks. They are leftover Lego pieces from the construction of the planets. But perhaps there will be something like Voyager that enters the solar system. We sent out a spacecraft that will exit the solar system eventually and perhaps get into other planetary systems. And we can imagine someone else, a neighbor, a technological civilization far from us, that sent a Voyager-like spacecraft a long time ago, perhaps 1 billion years ago, because most stars formed billions of years before the sun. And if such a spacecraft enters our solar system, we might recognize it as an interstellar object. So we found 3 interstellar objects over the past decade. What are they? The first one was almost a decade ago, on January 8th, 2014. It was a meteor an object that is 0.5 meter in size, roughly the size of a watermelon, that collided with Earth. So it appeared as a meteor, and I'll talk about it a little more. It had an unusual speed. It was faster than 95% of the stars near the sun, and also an unusual material strength and composition. And that hinted that it could be, for example, a Voyager-like object. And so I went on an expedition this summer to find out if there are any relics left over from this meteor. The second object was discovered by humans on October 19th, 2017. It was a much bigger object, the size of a football field. It was discovered by a telescope in Hawaii and was given the name Oumuamua, which means a scout in the Hawaiian language. It did not collide with Earth. It passed near Earth, and it had very strange properties, like it was flat in its shape. It was pushed away from the sun by some non-gravitational acceleration without showing any evaporation. There was no rocket effect the way comets have. And so the question was, what was pushing it? And it also originated from the local rest frame, the local standard of rest of the Milky Way galaxy. Very unusual. Only 1 in 500 stars are so much at rest in that frame as Oumuamua was. And then the third object was not unusual at all. It was just a comet that came from outside the solar system. It was given the name Borisov after the amateur astronomer Gennady Borisov, who discovered it. And that was on August 29th. 2019. So 3 objects were discovered over the past decade. The first 2 of them looked anomalous, not like the familiar rocks in the solar system. So that's intriguing. 2 out of 3. Interesting. So maybe we have a chance of finding a tennis ball that was thrown by a neighbor in our backyard. Now, what is an interstellar object? So let me explain. How do we know that it came from outside the solar system? Well, just imagine the sun in the middle here, this red object in the middle. The sun has a mass and it produces gravity. Now, if an object is moving fast enough, meaning above the threshold that is needed to escape from the sun's gravity, then it's not bound to the sun. That is an interstellar object. It's not gravitationally bound to the solar system. The Earth is. That's why for billions of years we are circling the sun. We are bound to it by gravity. But an object moving much faster than the Earth, actually not very much faster, just moving at 42 kilometers per second instead of 30 kilometers per second relative to the sun, would escape the gravity of the sun. Oumuamua was one such object. And as I mentioned, it had a flat shape, was pushed away from the sun by some mysterious force. And I suggested that it's just the sunlight that is pushing it. And for that, the object had to be very thin, like a sail. And nature doesn't make such objects. So I suggested maybe it's a surface layer that was manufactured by a civilization. And actually, a few weeks ago, there was a play that was presented for the first time at my home. It was written by the playwright Josh Ravech, who also wrote a play for Carrie Fisher and for Dick Van Dyke. And the name of the play about my work is A Piece of Sky. And the hope is that it will be presented in New York City next year. There are a few excerpts that I put here on this slide from the play. One of them is the question, why is childlike bullying more prevalent on social media than childlike curiosity? And it's not just social media, also in science. Another one is, my mother told me when I was born at the nursery that all other infants were looking at things in their cribs, but I was looking at the ceiling. I've yet to break that habit entirely. It gets me into trouble. And finally, my advice to young scientists, never pretend to be the adult in the room. Maintain your childhood curiosity. So in the context of that, I established the Galileo project more than 2 years ago to study objects near Earth that may have arrived from interstellar space and may represent technological gadgets. So we built an observatory at Harvard University that includes a number of instruments. Let me show you a short video showing them. Basically, it monitors the sky at all times.
Welcome to an overview of the Galileo Project's development site, codenamed Pigeon Run. Our instrumentation suite consists of both wide field and narrow field sensors. Wide field sensors are used for target selection and tracking, while narrow field sensors gather higher resolution data on potentially anomalous objects. Our main instrument is DALEC, a hemispherical array of 8 infrared cameras. Next to it is the ALCOR, a secondary high-resolution optical all-sky camera. Together, these instruments continuously monitor and track objects in the sky, analyzing them in real time for potential anomalous activity. This is AMOS, our acoustic monitoring omnidirectional system designed to detect and record acoustic signatures across the infrasonic, audible, and ultrasonic bands. AMOS also houses an ADS-B antenna for logging aircraft transponder data, allowing us to quickly separate known from unknown objects. Here we have Skywatch, a multi-static passive radar system designed to detect and track multiple objects simultaneously, measuring object positions and kinematics. And Pac-Man is an environmental monitoring system for measuring local weather conditions. Sensors include an anemometer, temperature and pressure sensors, a particle counter, and a flux gate magnetometer. Next up is Spectre, a radio spectrum analyzer with a wide band antenna for measuring radio and microwave emissions. Beacon is currently our only narrow field instrument. Beacon is a high-resolution pan-tilt zoom camera capable of 40 times optical zoom. Our instruments collect a wide range of data, all of which is fed to our computing enclosure housed beneath the DALEC and ALCOR instruments. Here, data is processed and analyzed in real time. Objects detected and tracked by the wide field instruments are localized in 3D space and analyzed for unusual characteristics. Selected targets are then sent to the Beacon PTZ for follow-up observation. Finally, data is recorded to disk and uploaded to the cloud via Starlink. These combined systems comprise the current version of the observatory class system, with many refinements, additions, and upgrades scheduled for near-term implementation at Pigeon Run.
So that was a brief overview of the project. And we're planning to extend the system in the future, put it in many different locations, and record unusual objects in the sky, because the US government is talking about unidentified anomalous phenomena, and we want to figure them out scientifically. We will not wait for the government to tell us what comes from outside the solar system. That's a scientific question, if there is anything. And we are also using satellite data to look at objects from above, not just from below. And currently we have 8 papers that we wrote about the observatory that is already functioning and collecting data as we speak. But what I would like to focus on in terms of my current work is on the study of this meteor that I mentioned, the first interstellar object that was detected by US government satellites from the fireball that it generated as a result of its friction with air. And I decided to lead an expedition to collect any fragments left over from this meteor to study their composition. It took place on June 14th to 28th this year, just a few months ago. And we hired a boat named the Silver Star. So let me show you some of the details. But before I get there, it all started from data that was compiled by NASA. But when we identified this object in the catalog of NASA, many of my colleagues argued that they don't believe the US government. And that was in 2019. And through my connections in government, I managed to get a letter from the US Space Command to NASA 3 years later, on March 2022, that confirmed at the 99.999% confidence that indeed this object from 2014 came from outside the solar system. You can see the letter on the left here. And so at that point, our paper, discovery paper, was published in the Astrophysical Journal. And the government also released the light curve of the fireball. It had 3 flares separated by 1/10 of a second. And when analyzing that data, we concluded that this object had material strength that was tougher than all 272 other meteors from the solar system that were cataloged by NASA over the past decade. So it was an outlier in material strength, tougher than iron meteorites. And the question is why? Why would the first interstellar meteor be tougher than all the space rocks that we know about from the solar system? And to find those fragments left over from it, we were able to narrow down the path of this meteor using data from a seismometer that recorded the sound from the explosion. Just based on the delay of the sound relative to the light, the way you do with a thunder following a lightning, we were able to tell how far away the explosion was. And you can see on the right-hand side, we managed to pinpoint the path of the meteor to a high precision. The seismometer was located at Manus Island in Papua New Guinea. So let me show you some photos from that expedition. Our ship was called the Silver Star, and that explains the tune, the song that you will hear in the background.
Drifting thinking I am where you are, drifting thinking I am.
So let me explain what we just saw. What you're looking at here is a team photo of the expedition crew, the 28 people or so. The expedition cost $1.5 million. This is the deck of the ship. Behind us, you see a large frame. This is called the A-frame, where we had a cable from the ship connecting it to a sled with magnets on both sides. and the cable length was about 3 miles. The sled was put on the ocean floor to collect any magnetic particles left over from this meteor. And the ocean depth is more than a mile at that location. We were surveying a region 7 miles in size. The ocean depth is 1 mile. And we were looking for particles that are roughly a millimeter in size, the size of a grain of sand. Just think about how challenging that is. So here are some photos. What you see in the middle and the right side are moments where we pulled the sled out of the water, brought it to the deck so that we can scrape the magnets from any magnetic particles that we found on the ocean floor. And what you see on the bottom left and middle is me jogging at sunrise. I jog every morning on land, and I repeated that routine also on the ship every morning at sunrise. We had a filming crew on the ship. There were 50 filmmakers and producers that wanted to be there. I selected one crew, and the director asked me one morning, "Can we film you jogging?" And I said, "Sure." They asked me to do 3 times the distance that I usually do, and it was of the order of 10 miles that I jogged that morning. But when I finished, the director said, "Avi, it looks like you're running. Are you running away from something or towards something?" And I said, "Both. I'm running away from some of my colleagues in academia who have very strong opinions without seeking evidence. And I'm running towards a higher intelligence in interstellar space." So here is an image of the sled that you can see at the top. And we were basically scraping any magnetic particles from it, using also a vacuum cleaner, as you can see in the bottom middle panel. And then we dried them up. We used a mesh with a size of 1/10 of a millimeter to filter out volcanic ash, which was very abundant on the ocean floor. This is black powder, tiny particles that we were not interested in because they were from volcanic activity on Earth. And then we were looking for bigger particles that may represent droplets molten off the surface of the object, the meteor, as it was exposed to the immense heat from the fireball that it generated as a result of its friction with air. So let me show you how the sled went on the ocean floor. You can see it from a video camera that was attached to it, basically like mowing the lawn. We went back and forth 26 times across a region 7 miles in size. And we collected magnetic particles on top of this muck, the mud that was on the ocean floor. It wasn't easy to keep the sled on the floor. At first, it was lifted by the cable, and it was basically kiting above the floor. And then we found a method of keeping it on the floor after the first day. But we collected a lot of volcanic ash, and after the 6th day, I wrote 43 diary reports. After the 6th day, I wrote a diary report on medium.com asking, where are the spherules? The spherules are these molten droplets from the meteor. We haven't found them after 6 days. So I was wondering, where are they? And on the 7th day, we found them. We found the first one, and I hugged the person that saw it first on the microscope. But here are the 26 runs that we had across the region. And the orange path is the path of the meteor. And ultimately, we found 50 spherules on the ship. And you can see how they look like here where the arrow points. They look like metallic marbles, very distinct from the sand in the background. And so we picked them with tweezers. They were roughly a fraction of a millimeter in size. And here are some images from the microscope. My daughter, when she saw those images, she asked me, could you put one of them on a necklace for me to wear? And I tried to explain to her that it's not possible because these are smaller than a millimeter in size. We can't thread them. And this is the delivery room. All these babies that we delivered, all these molten droplets were put in vials, and sort of the vials serve as their bed. In the delivery room, that is this plastic box that kept them together. And I shipped all the materials to my home by FedEx because I was not sure that they will not get lost at customs. So you can see here the suitcase that this black suitcase that arrived a few days after I returned home. And I realized that a few days of delay are not too much because it took probably billions of years for this material to arrive to Earth. And on the left, you see us on a rainy night searching for particles on the magnets of the sled. The person just to my right is the funder, Charles Hoskinson. And I brought those materials to the laboratory of my colleague at Harvard, Stein Jacobson, who is standing on the right here. He has a mass spectrometer among the best in the world. And on the left is my summer intern, Sophie Bergstrom, who found more than 600 additional spherules. Altogether, we have about 700 of them now. So I called her the spheral hunter. She found them using tweezers and a microscope after we brought the material back to Harvard. So these are images of what she found. And then we made a map of where these spherules were found per unit mass that was retrieved from the ocean floor. And in yellow, you see the regions of high yield. Purple is low yield. And we also, on the left, you can see a zoomed out image where we went to control regions that were far away from the meteor path. And there you see mostly purple. But when close to the meteor path, we saw an enhancement in the yield of spherules, suggesting that we were at the right place. There were additional extra spherules near the meteor path. So here are some images of how they look like. The inside of these spherules show evidence for smaller size spherules, sort of like Russian doll structure where you have spheres inside spheres. And the idea is that the small spheres solidified first, and then they were engulfed by molten iron that glued them together. Here is a spherule that looks like a soccer ball. And here is a more interesting one that is the merger of three spheres together. They didn't have a chance to become one spherical object because they solidified before that happened. And when we analyzed this material, this particular spherule that I showed last, which was in a yellow region, high yield region, potentially from the meteor, we found that it has an isotope ratio for iron that definitely implies that it came from outside of this Earth. It's definitely extraterrestrial. And then we studied the composition of elements in it. And here you see on the horizontal axis, the periodic table starting from lithium on the left, all the way to uranium on the right. And the abundances here are normalized relative relative to the standard solar composition, so the material that made the solar system. And what we found is that elements like beryllium, lanthanum, uranium have abundances that are hundreds of times larger than the standard composition of the solar system, meaning that they came from somewhere else. This abundance pattern does not match the rocks that we find on Earth, the Moon, Mars, or asteroids. And here are 5 spherules with this unusual, we call it belau, for beryllium, lanthanum, uranium composition. And here we show this composition as a function of the volatility of elements. And what it shows is that as elements become more volatile, in other words, they can be lost by evaporation during the airburst, during the explosion. Indeed, we are missing those elements on the right-hand side, implying that those belau spherules came from an airburst. So the question is, where did they come from? And one possibility is that they came from a molten lava planet, magma ocean. Actually, the Earth started this way when it was bombarded by heavy objects colliding with it. And then one of these collisions generated the moon. But the composition we find does not resemble the Earth. The idea is that when you have a molten magma, then some elements segregate to the core, the iron core of the planet. And those are the elements that we are missing. And the elements that are overabundant are those that are left behind in the crust of the planet. So that could explain the abundance pattern that we see, a molten magma ocean. But we don't find that composition in the solar system, so it must have been a magma ocean on a planet far away, outside the solar system. So where could it have originated? Well, I just posted a new paper yesterday, which could explain it. And the idea is that it could be a planet like the Earth that was created near a dwarf star. Turns out the sun is not the most typical star. Smaller stars are much more common. The nearest star has roughly 12% of the mass of the sun. It's called Proxima Centauri, and that is the most common type of star. And when you have a planet like the Earth near a dwarf star, turns out that the dwarf star can destroy the Earth if it comes too close to it. The sun cannot, because the sun is just too puffy, and the density of the sun, the average density of the sun, is less than the average density of the Earth. So it cannot destroy the Earth by gravity, by raising tides on Earth. But a dwarf star that is 10 times less massive than the sun is also 10 times smaller in size than the sun, and it's 100 times denser than the sun. And that's what it turns out to be. And so if you bring an Earth-like planet close to a dwarf star, it could destroy it. And so what would happen is that the planet will be spaghettified. It will be turned into a stream of rocks. And how can you get it? Well, planets are on orbits that can become unstable near dwarf stars because of another companion star next to the dwarf star that will kick the Earth-like planet towards the star. And so here is a simulation where we calculated with my postdoc, Morgan McLeod, what would happen to a planet that comes close to a dwarf star, planet like the Earth. And it will basically turn into a stream of rocks. And turns out that half of its mass will be ejected to interstellar space. And you ask, at what speed? Well, it turns out to be exactly the speed that was inferred for the first interstellar meteor, faster than 95% of the stars near the sun. And that coincidence to me was startling. I mean, I did the calculation 2 weeks ago on a piece of paper, and I realized, wow, that explains exactly the speed that we observed for this meteor. And I will not go into details, but we also find that the rate of impacts of such meteors on Earth is just the right one. If there are roughly 10 times the mass of the Earth in rocks near dwarf stars, then you get enough of them ejected to interstellar space such that one of them will collide with Earth every decade. One rock of 500 kilograms in mass, like this meteor, the interstellar meteor that we found. So altogether, there is, in this case of the meteor, there is a possibility of explaining it in terms of a natural origin. We are still not sure. And so we want to find bigger pieces of it to be sure whether it's natural or artificial in origin. But altogether, this interstellar expedition that we went with to the Pacific Ocean was risky. There were many potential failure points. For example, I might not have received the needed funding of $1.5 million. And then I could have not recruited the qualified engineers, navigators for the expedition. These were really the best in the world, the ones that came with me. And then we could have not built the proper tools to find those spherules. They may have not worked. The sled may have not stayed on the ocean floor. We might have not found magnetic spherules from this meteor on the ocean floor because perhaps the meteor didn't produce enough of them. And even if we found them, just separating them from the background was a challenge. And we might have not have access to state-of-the-art mass spectrometer because my colleague at Harvard, Stein Jacobson, could have said, I have other projects that I'm engaged in. I just don't have time to help you. And very thankfully, he was available with his team, and we discovered the Belau composition of extrasolar materials. So this just shows that taking risks in science pays off. And the next expedition that we are planning now is aiming to find larger pieces of this meteor to figure out if it was natural or technological in origin, because you can imagine that maybe uranium was enhanced because it's fuel in fission reactors, or maybe lanthanum was enhanced because it's a substrate for semiconductors. So to find out, we're going again to that region to look for bigger pieces. And of course, if it's a technological gadget, we might find buttons on it. And then the question is, should we press a button? That's it. Thank you so much, and I'll be glad to answer any questions you have.
Well, thank you so much for that really informative presentation. I think we all learned a lot about your research and your most recent expedition. We do have some questions coming in, so feel free to put your questions in the chat. Now, in my introduction with you, I said that you're author of 8 books, and we did have someone asking a little bit more about your books. Of your 8 books, I'm just curious from your perspective, for someone who may be new to reading about astrophysics or learning more about like extraterrestrial life and stuff like that, which of your books would you recommend for like the beginner who's just wanting to learn more?
Right. So I wrote my first book was by Princeton University Press, and it addressed the question, when did the first stars form in the universe? And I asked this question in anticipation of the Webb telescope, which allows us to find the first stars and galaxies in the universe. The scientific story of Genesis, the scientific version of the story of Genesis, we are all familiar with the biblical version, but we are able to now address the question of when was the first light produced. And according to what we know about the universe, there was a prediction, and we can now compare it to the data that is obtained by the Webb telescope. So if you want to understand the context of this question and what the Webb telescope is finding now, I would recommend my book. It's a short book, was written, published about 12 years ago. And after that, I wrote a textbook, much longer and more detailed, called the First Stars and Galaxies, the First Galaxies in the Universe. And that was also published by Princeton University Press. And now, more recently, I was mostly interested in the possibility of life elsewhere. And in addition to my book, Extraterrestrial, that came out in 2021, I also wrote a textbook, Life in the Cosmos, by Harvard University Press. And it's more than 1,000 pages long, and it gives all the information about the current search for life beyond Earth, both in terms of primitive forms of life, microbial life, and intelligent life. And it's a very comprehensive overview on this question. And of course, I'm also engaged in searching for objects that may have originated from a technological civilization, as I described.
Right. And, you know, it's kind of related, but Aaron, in the Q&A, he actually wants to know a little bit about your inspiration to study astrophysics. Was there a specific moment or something in your childhood or something that really drew you to it at the beginning?
Yeah, so actually, I was mostly interested in philosophy because it addresses the most fundamental questions about our existence at a young age. And I was driven into science by circumstances. I was born in Israel and had to serve in the military at a young age, at age 18. And in order to pursue intellectual work, the option that was given to me was to study physics because it's useful for the defense of the country. And I was recruited to a special program that allowed me to finish my PhD at age 24. And I studied physics. And then I was offered a position at the Institute for Advanced Study at Princeton, where Albert Einstein used to be faculty a few decades earlier. And it was a 5-year fellowship. I couldn't turn it down. And then after that, I received a faculty position at Harvard University. Again, I couldn't turn it down. Altogether, you know, I was offered these positions under the condition that I'll switch to astrophysics. And it felt like an arranged marriage. I always felt that I wanted to do something else, but these circumstances arranged this for me. But then later in my career, after I was tenured, I realized that even though it was an arranged marriage, I'm actually married to my true love, because I can address fundamental philosophical questions using the scientific method. So that's how I ended in astrophysics. It was not my choice to start with, but you know, I made the best lemonade out of the lemons that I was given in life.
Absolutely. And I was going to say, for those of people in the audience who have not read your most recent book, Interstellar, there is a lot of philosophy in this, really, about like humanity and how does humanity really become an interstellar species, knowing or being aware that we aren't necessarily alone out there. And so I really like the full philosophical discussions you had.
Well, I should comment on that, you know, the accomplished Nobel laureate physicist Steven Weinberg said towards the end of his book, the first 3 minutes, he said that the more the universe appears comprehensible to us, the more pointless it looks. And of course, what he was trying to argue is that religion has no place in our understanding of the universe. But when I look at this statement, that it, you know, I interpret it to mean that cosmologists are really focused on lifeless entities that have no life, like elementary particles, radiation, stars, galaxies, dark matter, you know. And obviously it looks pointless if you just focus on those. But just like in our personal life, if we find a partner, it gives a meaning to our existence. And so my point is that by finding a partner in our cosmic neighborhood, we will suddenly realize that we are not lonely, and we would get, by interacting with that neighbor, we will the universe will not appear to us as pointless anymore. And so that is my hope. That, in fact, I think many of my colleagues are misguided in just focusing on lifeless entities. And once we find the partners out there, neighbors in our cosmic street, we will feel that we belong to this universe, that there is a meaning, that we can actually ask them for what the cosmic play is about, because we just came at the end, just a few million years ago. That's one part in 10,000 of the age of the universe. We are not at the center of stage. If you arrive to a play and at the end of the play and you're not at the center of the stage, the play is not about you. And we have a hard time accepting that. We keep thinking that everything is about us. I'm not surprised, because I have two daughters. When they were young, they thought that the world centers on them, because they were at home and we paid a lot of attention to them. And of course, they had a psychological shock once they went to the kindergarten and found lots of kids, some of whom are smarter than they are. And so for us, it will be a psychological shock, but I think it will give us a sense of meaning to our cosmic existence.
Absolutely. I think that's a really deep thing to think about. All right, we're gonna kind of speed round some of these. We have a lot of like, do you know so and so? So we'll go through all of these. So first, Craig would like to know, have you spoken with Ohio's own Battelle, that's headquartered in Columbus, Ohio, regarding your Galileo project teams recently recovered sphericals from the bottom of the Pacific Ocean? If any corporate and government material science company knows about alien alloys, it's Battelle. And they also said thank you.
No, I did not. And I do not know if the government knows about anything alien, because I haven't seen any data or evidence that the government has in its possession materials from an alien city. So, the government is focused on national security. And frankly, what I don't care. I mean, for me, anything that says made in China is boring. I care about things that were made outside the solar system, okay? And the government is really not an organization that is supposed to tell us what lies outside the solar system. I will not go to President Biden and ask him, what do you think about the evolution of a red supergiant star outside the solar? Like, this is not what he cares about. So why would I go to a corporation and ask them, can you help me explain the science of something that I found? They don't know more than me. I'm a scientist that worked for decades on issues related to the universe. If they have in their possession anything from outside the solar system, I want to see it. Maybe I can help them.
Your book came out in like perfect timing, kind of, because it was very recent from all of the congressional hearings about extraterrestrial life, which dominated the news for quite a little bit, with both people who are skeptics and those who really do believe. What do you think the focus of those congressional hearings was about? And do you think, like, honestly, like, if there really are other life forms out there, I always think that, like, that can be a really scary thing for us on Earth to like grapple from a philosophical perspective. So, like, how do you think it should be addressed? Maybe I don't know if I'm wording that clearly enough.
Well, it was difficult for people to recognize that the Earth is not at the center of the universe. So what? So what? I mean, eventually we realized we are not. Okay, the Earth moves around the sun, and people got used to it. I'm not, my job is not to be a therapist to help people cope with facts. My job is to find the facts. So if we have neighbors, people will have to get used to it. Whether you sit in your home, you shut off the windows, you don't want to hear about it, doesn't matter. You will still have the same neighbors. You can ignore it. You can just avoid looking through the windows and believe in some fictional or virtual reality. But who cares? I mean, the neighbors will still be out there. As Galileo said, the Earth continues to move around the sun. That the fact that they put Galileo in house arrest and refused to admit that the Earth is moving around the sun didn't change anything about the orbit of the Earth around the sun. I want to find the facts. I don't care about how people react to those facts. I mean, just think about the World Cup, the Women's World Cup, where teams were competing with each other, okay? And there was a question of whether the ball passed, entered the goal. And of course, it was devastating news for the US soccer team to hear that they lost. So you would say, okay, well, should we think about the response of the players to the fact that they lose? And maybe we should moderate that and not tell them, no. What FIFA did was use video cameras to record what happened. They didn't go to ask the players. They didn't ask the spectators, the people looking at the game, what really happened. How do you accept that? Will it hurt your feelings? What FIFA did was use video cameras and monitor the ball and see whether there was a goal. And whatever the outcome is, that was accepted as the fact, the conclusion of the game. And a lot of people were upset about the outcome. But that didn't change the way FIFA decided the game ended. Okay, so science is done the same way. You collect evidence through instruments. And whatever the instruments tell you, it's just like a detective story. These are clues that should guide you. Now, of course, you can go and ask people. You can put people in the House of Representatives that will express their opinions. There will be pilots. There will be David Grush who says, I spoke with 40 people and they told me this and that. And I say that is not evidence. The fact that you spoke with 40 people, I mean, that could be used in a, in the legal system, because very often eyewitness testimonies are being used there. But we know from car accidents that people that are involved in the car accidents report very different things. And how can, different people report different things if they were witnessing the same event? It's because, humans are, they have biases, they could be fooled. And so humans are not scientific instruments. And the response of humans to facts is not my, expertise. That's the expertise of psychologists, psychiatrists. That's not really what I care about. I want to know the facts, okay? And those facts are being recorded by instruments that have no personality. That's the way science is done. Now, in the hearing that we heard at the House of Representatives, we didn't see any evidence. It was all people talking about what they saw. And that's not evidence for science. That's not a scientific quality evidence. So I haven't seen convincing evidence as of yet. It's possible that the US government has it. But it's also possible that David Grush spoke with 40 people and they told him stories. And these stories have nothing to do with facts. And so in order to be convinced that there is something behind those stories, we need to see the evidence. We need to see the materials from alien spacecraft, the way he described it. And one way to approach it is to say, okay, let's wait for the government to declassify the information it has, assuming that it has something. But, it's just like waiting for Godot in Samuel Beckett's play. You could wait forever. And another approach is to say, the sky is not classified. The oceans are not classified. We can just find the evidence ourselves. Why should we wait for the US government to tell us what lies beyond the solar system? We can figure it out as scientists using our instruments, not what people tell us. And so that is the path that I'm taking. And the hope is that we will know more in the coming years, thanks to the Galileo project.
Absolutely. And I'm glad that you brought that up, because we did have someone who wanted to know, what resources do you recommend for anyone watching tonight who wants to keep current on the newest trends, research, and developments in your field?
Right. So I have a place on medium.com. If you just search for Avi Loeb at medium.com, you will see essays that I post every few days with updates about my research. And for example, there were 43 diary reports written during the expedition. They were read by millions of people around the world. They were translated to Spanish. There was a huge number of followers, and people told me that they were thrilled to read those because it gave them a first hand encounter with how science is done, because most of the time the way you hear about science is by a press conference where the scientists just report about the results, but they don't show you the process, which is basically associated with searching for evidence, trial and error, making mistakes. That's part of the scientific process, and I was describing it in those diary reports, and I describe it in my on medium.com. So that's one place. And of course, you can also follow scientific papers, but that's a little more technical. So on the subject that I described today, the Galileo project, perhaps the medium.com essays are the easiest way for the public to learn about the developments on a weekly basis.
Right. And I think that would be a great resource. I know I looked into it before tonight's presentation. So I just want to say thank you so much. I know we have more questions, but we're pretty much at 8 o'clock. So thank you so much to everybody. Don't forget, Interstellar is available. I have the audiobook here. We do have it available through the Learn It Owl. We do have copies at the library. Avi, thank you so much tonight for spending an hour with us and sharing your expertise and knowledge. And if you go on future expeditions, I hope you find and uncover even more fantastic research.
Thank you for having me. It was a great pleasure.
Thank you. Thank you so much, everyone, and have a great evening. Good night.